This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, everybody, let's make a start. First of all, thanks for sticking around on a very cold, wet Wednesday afternoon. What I'd like to do today is just finish off with the ionic structures, and from there we're going to talk a little bit about silicate structures, and then finally we're going to finish up talking about the structures of elements. Okay, so we were touching on this in our lecture on Monday, and this is the structure of zinc sulphide. And we said that there were two crystalline forms, and you need to be aware of both of them. They are zinc blende and wurtzite, but they both have the formula ZNS. And before we get started, it's worth just looking at the relative size of the radii there, and we can see that zinc 2 plus is about 35% the size of the sulphide ion in terms of radius. So as a consequence of that, because it's so small, it will fit into the tetrahedral holes. Now it turns out it's a little bit too big for the tetrahedral hole, so it has to push the sulphide ions apart slightly to be accommodated. And you might say, well, why doesn't it go into the bigger octahedral holes? Well, if it does that, it'll rattle around, it won't make contact. So it needs to go into a site where it's going to make contact with all of the sulphide ions. Okay, so zinc blende is a face-centred cubic array of sulphide ions with 1/2 of the tetrahedral sites filled with zinc. The reason it's 1/2 is that there are 2 tetrahedral sites for every sulphide ion. Okay, so if there are 2 tetrahedral sites, but there's only 1 zinc for every sulphide, only half the sites get filled. Now wurtzite is very similar, but instead of the sulphide ions being arranged in a face-centred cubic arrangement, or cubic close-packed, they're arranged in a hexagonally close-packed arrangement. Otherwise, the structure is the same. 1/2 of the tetrahedral sites, again, are occupied. Okay, so there's the structure of zinc blende. And you'll notice that we've got the sulphides here, the corners of the unit cell. Notice that the sulphides are actually located at the actual intersection of the axes of the unit cell. That's the centre of the sulphides there. And you can see that we've got a tetrahedral site at the front here, surrounded by 1, 2, 3, 4 sulphides. There's a tetrahedral site behind here, surrounded by the one at the back, one at the top, one at the back and one at the side. That tetrahedral site is empty. The one at the back here is filled, the one at the front here is empty. So what you could do, you could actually imagine dividing up that face-centred cubic unit cell into 8 little cubelets. Okay, so if I take a cublet from here to there, to the middle point, halfway along that edge, that'd be the top half, down here to the centre, to the front, across here, and that little cublet at its centre is a tetrahedral site. For the cublet behind, it's empty. So every second cublet is occupied by a zinc in that particular case. The coordination number of the sulphur is 4. The coordination number of the zinc is also 4. And it doesn't matter whether really we say it's a face-centred cubic arrangement of zincs with the sulphurs in the tetrahedral site, or it's a face-centred cubic arrangement of sulphurs with the zinc in the tetrahedral site. So here's 2 unit cells displaced from each other. The black white line here corresponds to the face-centred cubic arrangement of the zincs. The green one is the face-centred cubic arrangement of the sulphur is emphasised there. Okay, so that's zinc blend. There's the space filling model. Do you remember what I said about the sulphides not touching? Because the zincs are just a little bit too big for that tetrahedral site, so just push the sulphurs apart there in that particular case. Okay. This is the octahedral site here. That space in there, halfway along each edge is the octahedral site. There's also an octahedral site at the middle of the unit cell. But you can see that octahedral site is way too big to accommodate the zinc 2+. Now, this is the vert site structure, hexagonally close packed, and we've got the A, B layers there. The unit cell is more complicated, and I don't expect you to know the unit cell for vert site. Okay, it's actually, the axes are not orthogonal as they are for zinc blend. But what I do want you to be aware of is that we have A, B layers, and in between them we have these tetrahedral sites. Now there are empty tetrahedral sites, just as we had in the zinc blend. If I look at that sulphur here, that one, and these three at the base, there's a tetrahedral site just here which is empty. Okay? Do we have octahedral sites? Yep. Let's see if we can find one of those. If we take those three up here and those three below, there's an octahedral site right in the middle there. It's empty. Again, because the zinc is too small to occupy an octahedral site. Okay. So, what happens if the ions are about the same size? So we said before, if the cation's really small, it goes to the tetrahedral site. If the cation's a bit larger, it can go to the octahedral site. But what if the cation is a comparable size to the anion, as we would have in the case of cesium chloride? What happens then? Well, it turns out that rather than have close packing of spheres, we have a simple cubic packing of spheres. So in this case, we don't have close packing. It's neither hexagonal close packing or cubic close packing. It's what we call simple cubic or primitive cubic. And so in this case, I've got these green spheres, which represent chloride ions, at the corners of the unit cell. And in the middle there, I've got the cesium ion. So now the coordination number is 8. I've got 8 chlorides around that cesium. But it's not a close packed structure. So why does that happen? It's because those two radii are similar to each other. The radius ratio is 0.93. So if the cation's much smaller than the anion, tetrahedral sites. If it's a bit bigger, octahedral sites. If they're about equal size, we go to a different type of packing. We go to this simple cubic packing. Okay, what about the environment of the chlorides? Well, another way we can describe that structure is to put the chloride at the centre of that unit cell and have cesiums at the corner. And they're equal descriptions. Now, we covered early on body-centred cubic. Do you remember talking about that? Where we had atoms at the corners of a cube and then one right in the middle. That looks like body-centred cubic, but it isn't. And that's because to be truly body-centred cubic, the atom we have at the middle has to be the same as the atom we have at the corners. This is different. So we say this is simple cubic, not body-centred cubic. Okay, so here's an example of 8 unit cells. So here's this cube here, that's one unit cell there. And then you can see we've got the chlorides at the corners, and then right in the middle there, we've got our cesium ion in that particular case. If I just focus in on the cesium ion, we've got 8 here, 1, 2, 3, 4, 5, 6, 7, 8. They are sitting at the corners of a cube. And then in the middle of that cube, I've got a chloride ion. Okay, so there's the two ways that we can look at the structure, either simple cubic arrangement of chlorides with cesium in the cubic holes, or a simple cubic array of cesiums with the chlorides in the cubic holes. All right, let's look at one last structure. This is a structure that I expect you to know. In fact, those 5 structures you need to be on top of. You need to know sodium chloride, zinc blend, wurtzite, cesium chloride, and this is the last one, calcium fluoride. Okay, so it's similar in some respects to cesium chloride in that the radius ratio is close to 1, 0.752, it's getting towards 1. So we're not going to get close packing with octahedral sites filled in this particular case. What happened with cesium chloride? We got simple cubic packing, and then we had the cubic holes occupied. And this is what happens here. We've got, in this case, the fluorides forming this simple cubic arrangement. So here's a cube of fluorides, and we put a calcium in the middle. But because of the ratio, because there's only half as many calciums as fluorines, half of the cubic holes are empty. All right, so it's like cesium chloride, but we take away half of the cations. So this little cubic hole at the back there, empty. This one filled, the one at the front here, empty. Half the cubic holes are filled with cations in that case there. Why do we get that arrangement? Because the radii are similar. Okay, so if I was to extend this structure out, what we would find is that, and looked at the calciums, what we would find is that the structure actually looks like that. And if we just concentrate on the calcium positions, the calciums turn out to be at the corners of a cube and also in the middle of each face. You see that? The calciums are at the corners and also the middle of each face. The calciums are face-centered cubic. Now, what about the fluorides? Well, it turns out we can think about the fluorides sitting in tetrahedral holes. So there's a tetrahedral hole, filled. The one at the back, filled. One over here, filled. All of the tetrahedral sites are filled because there are twice as many fluorides as calciums, and so all of those tetrahedral sites get filled. Now you might look at that and say, hold on, this goes against everything we said, because this should be too big for a tetrahedral site. And that's true. But what happens is these calciums are arranged so that they are so far apart from each other, they're not touching. So this is a face-centered cubic arrangement, but it's not really fair to say that they're close packing. Okay. So there's a big separation between those calcium ions there. Okay, so if I wanted to look at those, you might say, well, where are those cubic holes we spoke about before? If you take those 8 fluorides, 1, 2, 3, 4, 5, 6, 7, 8, there's a cubic hole in the middle here. No calciums in there. But if I went across to the next unit cell, I've got 1, 2, 3, 4 fluorides there, and another 4 over here. 1, 2, 3, 4, which would give me a cubic environment around that calcium there. So, 2 ways that I can describe the structure of calcium fluoride. A simple cubic arrangement of fluorides with half the cubic holes filled with calciums, or a face-centered cubic arrangement of calciums with all of the tetrahedral sites occupied. If you're presented with the structure like that, what I expect you to be able to do, if I gave you the cell length, I expect you to be able to work out the closest distance of a calcium to that calcium there. How would you do that? Well, if you know that cell length there and you know that cell length there, then using Pythagoras, you could actually work out the face diagonal distance. Half the face diagonal will be the centre of that calcium to the centre of that calcium. I expect you to be able to do that calculation. Okay? Is that clear to everybody? I expect you to be able to do that calculation. What if I said to you, what's the separation between the fluoride ions? Okay? Well, that fluoride there is level with about a quarter of the way along that axis there. That's 3/4 of the way along. So between here and here is half the unit cell length. So if I know the unit cell length, I know that the fluorides are half that separation apart. Okay, make sure you can do that calculation. Okay, there's the space filling model for the calcium fluoride, and you can see that the calciums are a long way from making contact with each other, and that's because the fluorides are so large. But nevertheless, it's convenient to think about this structure in terms of a face-centered cubic arrangement of calciums, fluorides in the tetrahedral holes. You need to know that the coordination number of the fluorides is 4. So if we take this fluoride here, it's got 1, 2, 3, 4 calciums around it. The coordination number of the calciums is 8. So let's look at this calcium here. It's got 1, 2, 3, 4 fluorides here. In the next unit cell, there'll be another 4 there. So the coordination number of the calcium is 8, and it's in a cubic environment. Okay, just a quick summary. In fact, I've put a summary sheet on the LMS which you might like to download. So in the where the lecture slides are, there's a summary sheet for what you need to know for these particular structures. But in close packed structures, hexagonally close packed, cubic close packed, there is 1 octahedral site and 2 tetrahedral sites for every sphere. Another important point is that the radius ratio of ions influence the type of structure that are obtained. And finally, while many structures have close packed arrangements, the spheres that do the close packing don't always touch. Okay. All right, let's leave that there. And what I'd like to do is to move on to this lecture here. And we might just start off with a little quiz, just to make sure we're on top of that. So if you've got your quick poll device there, I'll just see if I can work this, how to do this. Put that onto there. Is that going to work? Should do. Okay, good. Okay, so first question. How many calcium ions are in the face-centered cubic unit cell of calcium fluoride? So if you want to get onto the device with that web address, we can even try the QR scan there. Then answer, how many calcium ions are in the face-centered cubic unit cell of calcium fluoride? Give you 15 more seconds. Don't be afraid to ask your friend. Make sure your friend, though, is smarter than you are. Okay, 5, 4, 3, 2, 1. Okay, let's see how people voted. Okay, so we had 31 respondees, a couple of late voters there, a few more late voters, 38 responses, and the most popular one is B. So how many calcium ions are in the face-centered cubic unit cell? So the calcium ions are at the corners of the unit cell. If we have an atom at the corner, then 1/8 of its volume is inside that unit cell. 8 times an eighth is 1. Plus we have the calciums in the middle of each face. If they're in the middle of each face, they're shared between 2 unit cells, so half of their volume is inside that unit cell, and we have 6 faces. 6 times a half is 3, plus 8 times an eighth is 1, a total of 4. So the answer to that is B, which was the most popular response with 45%, and the late voters, fantastic to see, picked the right answer. Okay, let's clear that. Let's look at the next question. How many fluoride ions are in the face-centered cubic unit cell of calcium fluoride? How many fluoride ions are in the face-centered cubic unit cell? For 10 more seconds. 5, 4, 3, 2, 1. Vote now. Okay, so most have gone for C, but it's close between B and C. 43% have gone for C. So there's a couple of ways that we can work this one out. What we can do is just think about the fact that if we had 4 calciums in there, and given that the unit cell is representative of the whole structure, and we know it's CaF2, if there are 4 calciums, there must be 8 fluorides. And you might remember we said that we can divide that face-centered cubic unit cell into little cubelets, 8 little cubelets. And now each cublet has got a fluoride ion at the centre. Okay, so those fluorides are completely inside the 1 unit cell. So there's 8 is the answer there. And so the most popular answer there is C, and quite a few more people got that right after I told them the answer, which is good. Answer is C. Okay, let's go to a new poll. What fraction of the tetrahedral sites are filled in zinc blend? What fraction of the tetrahedral sites are filled in zinc blend? Okay, 10 seconds. 5, 4, 3, 2, 1. Last chance to vote. And we've gone for 72%. Have gone for C. And back to 70% there. Okay. So for zinc blend, we've got 1 zinc for every sulphur, and we know that there's 2 tetrahedral sites for every sulphide ion. So if there's 2 tetrahedral sites for every sulphide ion, but there's only 1 zinc per sulphide ion, then half of them must be filled. So the answer is C. Congratulations to the people who picked E too. It's a very brave choice given that E isn't an option, so well done. Okay, please don't do that on the exam, okay? That's very important. Okay, let's get back to this lecture. I'll just see if I can manage to bring that up. Okay, so what I want to do now is to move on to other extended structures, but rather than looking at ionic structures, we're now going to look at extended networks in which we largely have covalent interactions occurring. Okay, so these are examples of what we call network solids. So this compound here is this is the structure of quartz, silicon dioxide, one of the forms of silicon dioxide. and that's the most stable form of quartz at room temperature. And what I'd like you to be aware of here, and this is common to all silicate structures, is that we have a silicon and it's bound to 4 oxygens. And those 4 oxygens are located at the vertices of a tetrahedron. So every silicon is in a tetrahedral environment of oxygens. So the silicon is 4 coordinate. The oxygen, on the other hand, only connects to a maximum of 2 silicons. So here's an oxygen, and you can see it bridges 2 silicons, and there's a bit of a bend at that oxygen. The angle's about 144 degrees in that case there. Okay? And that gives us this beautiful 3-dimensional network. It's actually a chiral network. It actually has helices in it. And if you've got a helix and all the helices run in the same direction, then it will be chiral. So if I take that silicon just there, the one I'm pointing at, and we just follow that down. So we go to the oxygen, the silicon, to the oxygen, to the silicon, to the oxygens behind there, to the silicon, which is directly behind that silicon we started with. So if we have a helical structure, and all the helices run in the same direction, then we have a chiral material, chiral network, if you like. Okay, so we're often told in chemistry that there is a similarity in the behaviour of elements as we go down the group. But one place where that falls down badly is when we compare carbon dioxide to silicon dioxide. In fact, there is an incredible contrast in their properties. Carbon dioxide, as we're aware, is a gas under normal conditions, whereas silicon dioxide is a very high melting point solid. Why is that? Well, it's because silicon and oxygen do not form stable double bonds. So if we consider carbon dioxide, we can get a nice effect of overlap between the p orbitals on the carbon and the p orbitals on the oxygen. But that overlap of p orbitals is less effective for silicon and oxygen. The atoms are further apart, the side-on-side-on overlap, the pi bonding of those p orbitals is not so strong. And so rather than getting a double bond, we have each silicon bound to 4 oxygens and each oxygen bound to 2 silicons. Okay, so what we're going to do is talk about silicates. So if we add ATE to the end, that's telling us this is an anionic system. And we're going to look at the way that we can take silicon surrounded by 4 oxygens and link them together to make different structures. Now these are really important because they make up the bulk of the Earth's rocks and minerals in the crust. And we can consider silicates to be oxyanions. And sometimes these structures can be oligomeric, which means they've got a few units stuck together, or they can be polymeric, forming very large structures. And to balance the charge on these silicates, we often have metal ions present as well. Now, the best way to understand it is in terms of this building block here. So what I've got here is a silicon bound to 4 oxygens, each of which has a negative charge. And that's our basic building block for these silicate networks. Now we're going to be drawing extended structures, and what we can do is come up with a shorthand way of representing that structure. And so rather than write out that type of structure each time, what we can do is to represent that unit by this tetrahedron. So it looks like an equilateral triangle with 3 lines linking in the middle, but what it's supposed to be is a tetrahedron viewed from on top. And each vertex here, 1, 2, 3, 4, represents one of those oxygen atoms from the SiO4 unit. So that represents an oxygen, that represents an oxygen, oxygen, oxygen. You might ask, where's the silicon? That's buried inside that tetrahedron. Okay? So, how does this work? Well, let's look at a simple disilicon network. This anion here, Si2O7. So here we've got a silicon and it's bridged by an oxygen to another silicon. You notice that when we have the oxygen bridging, there's no charge. If the oxygen is terminal, as we have here, it carries a negative charge. Okay, so it's important to keep that in mind. So that's our Si2O7. You can see it's got a 6 minus charge just by adding up the negative charges there. And we can represent it as we've done there. We have corner-sharing tetrahedra, which means that that oxygen here is common to both tetrahedra, in that case there. So you need to be able to look at that type of representation and say, oh, okay, there's 2 tetrahedra, therefore it's 2 silicons. How many oxygens are there? Let's just count the vertices. 1, 2, 3, 4, 5, 6, 7. Total charge? Well, we have 6 terminal oxygens. 1, 2, 3, 4, 5, 6. Alternatively, I can work out the charge by recognising that silicon is in the +4 oxidation state and oxygen is in the -2. So if I have Si2O7, 2 times +4 is +8, and 7 times -2 is -14. -14 plus 8 gives me a net charge of 6 minus. So you should be able to look at those sorts of representations, work out charges, work out formulas. Okay, this is one of the simplest types of silicates we can have, where we just have a discrete SiO4 unit, something in zircon. The Zr4 plus is the counter ion for that SiO4 unit. The garnet, which is a gemstone, that also has these SiO4 units as isolated structures. If we look at something like jade, we've got these polymeric silicate chains. And this is just a section of that polymeric silicate chain. It's not the complete structure. That goes on and on over here and on over there. So that's a ball and stick representation. And this is how we would represent it in terms of those tetrahedra. So you can see that each tetrahedra links to 2 other tetrahedra. So that would represent these 2 oxygens here, that point and that point, like that. That terminal oxygen here and that terminal oxygen are those 2 there. All right, so how do we work out the overall formula? Well, what we can do in this case is just look at the repeating unit. The repeating unit is one of these SiO4s. Now that silicon there owns those 2 oxygens. So that silicon has 1 oxygen, 2 oxygens, and it shares these 2. So it owns half of that one and owns half of that one. So it's 1 silicon and 3 oxygens, SiO3. What about the charge? Well, per silicon, we've got 2 terminal oxygens, each with a minus charge, so it's a 2 minus charge. It's SiO3 2 minus. Or alternatively, I can recognise that silicon's +4, each oxygen is -2, 3 times -2 is -6, +4 gives me a net charge of 2 minus. Okay, so if I presented you with that structure there, I'd expect you to be able to come up with a formula for it. This is a double chain that we have here, and this is a form of asbestos. It's known as the mineral tremolite. And this is a little bit more complicated because there's 2 types of silicon here. We have a silicon like this one in which we have 2 terminal oxygens and 2 bridging oxygens. And this silicon here where we have 1, 2, 3 bridging and 1 terminal. How do we work out the formula for that type of structure? Well, what I can do, remember this is not extending out here, this is the end of it, it's just a double chain. I take an arbitrary point along the chain, draw a line. And then I go along the chain and I'm looking for a point which is identical to that. So I've got a bond from the silicon to oxygen going in that direction. Come all the way, there it is. That's the repeat unit. Do the same down here. I'm looking for that unit there, repeated, there it is, and I draw a box around it. And now I count up the contents of that box. So, how many silicons? 1, 2, 3, 4. So it's Si4. How many oxygens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So Si4O11. What about the charge? Just do your simple arithmetic. 4 times plus 4 is plus 16. 11 times minus 2 is minus 22. Overall charge minus 6. If it's right, I should have 6 terminal oxygens. How many do I have? 1, 2, 3, 4, 5, 6. So it's Si4O11 6 minus. So quite a nasty mineral, that one. That's how we would represent it in the polyhedral case. But this was a very, very widely used building material. In fact, lots of houses still have lots of asbestos still in it. But when it's in its fine fibrous form, it can be inhaled and it can get into the lining of the lungs and cause a constant irritation. And over years, that constant irritation, because it can't be broken down by the body, can result in cancer. And there's a specific type of cancer that emerges from this, and that's mesothelioma. Okay, so it was very big in the news going back a few years ago now, but a lot of people who have mesothelioma have been exposed to asbestos. Very stable compound which the body can't break down. Okay. We can also have ring structures. So SiO4 units can be arranged in a ring, and this is an example here of beryl. And here we've got our ring structure there. We've got 6 silicons, and each silicon has associated with it 1, 2 terminal oxygens and 2 bridging oxygens. So it's SiO3. But because there's 6 silicons, it's Si6O18. Total charge? Well, 6 times plus 4 is 24, and we've got 18 times minus 2 is minus 36. Net charge is 12 minus. Or I can just count up the number of terminal oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's how we would represent it in terms of the tetrahedra. Okay, we can also have sheet structures. So what we're doing here is we're going from that single unit where no oxygens were bridging to going to the chain, to the double chain, to the sheet, is that we're reducing the number of terminal oxygens. So when I have my sheet structure, I'm going to have 3 out of the 4 oxygens are going to be bridging. So this is the formula for talc, and some of you might be aware of talcum powder. It's a very slippery sort of white material, very good at absorbing moisture, and that's because water can slip in between these layers. It's slippery because it's a layer structure and those layers could slide past each other. Okay, so what does that look like? It looks like that one there. Now you can go through that same routine and try and count the atoms, but what I think is a better way to do here, recognising that all silicons are the same, we just concentrate on, say, this silicon here. So, how many oxygens are bridging? 1, 2, 3. 3 times a half? 1.5. 1 terminal, so that's a total of 2.5 oxygens per silicon, which is Si2O5 or Si4O10. So what we've done there, you can actually trace out a repeating unit there. That's a little bit harder to find, but you can come up with the same formula. If we write it as Si4O10, then it's a 4 minus charge, because there's 1 terminal oxygen on each silicon in that case there. Si4 gives us plus 16, O10 gives us minus 20, net charge is minus 4. So what we've done in going from the isolated silicate ion through to the chain, through to the sheet, is that we're decreasing the number of terminal oxygens. And then finally we get to the case where all oxygens are bridging, there's no charge, and we get back to quartz. Okay, and that's what we have there. Most sensational crystals, quartz. They're just wonderful. There's lots of those new age shops around where they talk about the magic healing power of crystals. If you look in their windows, they often have quartz crystals there, and if you just spend some time looking at them, they are absolutely spectacular. Really beautiful crystals. Not sure about the magic healing powers though. Okay, so metal silicates, they tend to, often if we try and crystallise them in the laboratory, they cool too quickly to actually form crystals, and what happens is we often will form a glass. Okay, so if we start to form a glass, then we don't get our crystalline arrangement, we get this disordered arrangement. It's a little bit like the same you might have with toffees. Toffees not as popular as they used to be when I was a kid. Kids used to bring to school these toffees which were just a solidified sugar solution. So they'd heat up this water, have it saturated with sugar, and if they cooled it really quickly, it gave us this glassy, very hard product which was outstanding for breaking off your teeth. Okay? Same thing's happening here with glass. If we cool it quickly, we get the glass. If we allow it to cool very slowly, like what happened in the Earth's crust over a long period of time, then you can get crystals of things like quartz. Okay, over time, glass can be converted into crystals, and that can be disastrous if you've got windows. This is soda glass. This is the most common type of glass where you have a glass bottle. That's the formula of it. It contains sodium silicate, calcium silicate, and silica all mixed in together there. That's not such a good glass for working in the laboratory or for doing any cooking. And that's because of the thermal expansion. It's got a high coefficient of thermal expansion, which means if I heat it up, the glass expands. Now if I don't do that evenly, then some part of the glass vessel will expand much quicker than other parts, and that will lead to the glass breaking. If we actually add B2O3, borates to it, that has the effect of lowering the coefficient of thermal expansion, and we can heat up the glass and we don't get cracking occurring. So glassware is safe to use in the laboratory. Okay, what I'm going to do now, and probably won't get as far as I would have hoped with this, is that I want to look at the structures of the elements, because if we look at the structures, it's a nice way of trying to understand the chemistry of the elements. And we're going to start off with element number 1. We'll work our way through all of the elements of the periodic table. So element number 1 exists as H2, simple diatomic molecule. If you look at the position of hydrogen in the periodic table, you might think, well, should it be like lithium, sodium, potassium? Should it have metallic type character? Well, it turns out if you put it under enormous pressure, 3 million atmospheres, it will transform into a solid and it will exhibit that type of metallic character. Hydrogen's important because it forms more compounds than any other element. And maybe in your lifetime you might see hydrogen replacing fossil fuels for onboard storage of energy. Okay, one element down, about 114 to go. Let's put all the noble gases together because they have a similar chemistry. Monoatomic gases under normal conditions. And if we look at the boiling points, we can see as we increase the number of electrons, we increase the boiling point. We're increasing the dispersion forces. The polarisability of these atoms is increasing. The dispersion forces increase as well. what if we cool these gases to a solid? We can consider those atoms to be spheres. What do they end up doing? Well, it turns out that they pack together in cubic close packed arrangements. Well, neon, argon, krypton and xenon do. They have that packing arrangement. So it doesn't matter whether it's metallic bonding or ionic bonding or dispersion forces. Spheres like to pack in a close packed arrangement. Helium does some really weird things depending upon which isotope it is too. It can actually change the type of structure you get. In fact, there's lots of really nice YouTube videos of the weird things that helium does. Okay, so how many elements is that? It's about 7 elements so far. We better keep going. What we're going to do is cheat now, and we're going to lump all the metals together because they all have a similar type of packing. And 75% of the elements in the periodic table are metals. So all of these guys here, plus the F block, are all metals. And for those metals, we often have body-centered cubic, cubic close packing, or hexagonal close packing. So this is a slide that we used earlier on. The close packing is a little bit more dense than the body-centered cubic, but those metals adopt one of those types of structures. Okay, let's move on to this guy, boron. We don't hear much about boron, but it's a fascinating element. So why is it so interesting? Because if it's electron configuration, let's look at this. 2s2, 2p1. 3 valence electrons. But how many electrons are in that valence shell? Sorry, how many orbitals are in that valence shell? There's 4. And s and 3p. So boron's got a problem because it's got more orbitals in its valence shell than electrons. Now normally, atoms in that position have metallic type bonding. But boron is a non-metal. It's small, it's high up in the periodic table, so its metallic character is low. So it's very frustrated, boron, because it's trying to arrange itself in a way which can solve the problem of having more orbitals than electrons in its valence shell. And so it adopts many different types of form, but common to many of these forms are these B12 units. Now this is an icosahedron here. And what boron does is arrange itself so that it's at the vertices of this icosahedron there. So the icosahedron has a point up here, 5 in this plane here, another 5 in that plane there, and 1 down there. But in that type of arrangement, it tries to solve the problem of having more valence orbitals than valence electrons. So what do you need to be aware of? You need to be aware of that this B12 unit is quite common for boron. Okay? Make sure you remember that. Let's talk about carbon now. And many of us have heard about the allotropes of carbon before. There's all of these types here. This one you might not have heard of before, Lonsdale light. But we have very different properties. And one of the main points I want to make here is that it's not so much the identity of the element, but rather its structure, which is responsible for its properties. Now, diamond and Lonsdale light both involve tetrahedral carbon atoms, sp3 hybridised. The graphite and the fullerenes involve trigonal carbon atoms. Let's look at diamond in this case. And we've got a carbon atom with 4 equivalent carbon-carbon bonds, and the angle here is the perfect tetrahedral angle, about 109.5 degrees. Now, if I just take a tetrahedra and I just start sticking them together without thinking, will I get diamond? Will diamond be the inevitable consequence of packing them together like that? Okay, well, here's the structure of diamond. Here's the tetrahedral carbon atoms, and within the structure of diamond there's a repeat unit. This is actually a hydrocarbon known as adamantane. And in adamantane you can see actually these cyclohexane type rings all in chair conformation, see that? 4 fused cyclohexane type rings. If we have that adamantane type unit in the extended structure, then it is likely to be diamond. Okay, so how can we be sure we're going to get diamond? If we take the tetrahedral centres and we link them together and we make sure that along any carbon-carbon bond, the bonds are perfectly staggered. If the bonds are perfectly staggered, then diamond is the inevitable consequence. Okay. Another way that we can think about the structure of diamond is to relate it to cubic close packing. So if I take a cubic close packed array of carbon atoms and I put carbon in half the tetrahedral sites, I get diamond. So carbon doing the face-centred cubic arrangement, but also being in half the tetrahedral sites, much like we said for zinc blend, then we get diamond. You might say, where's that adamantane unit? Well, here's one cyclohexane type ring, 1, 2, 3, and 4. So the unit cell may be considered as a close packed arrangement of carbon atoms with carbon atoms in half the tetrahedral sites. If I took zinc blend, changed all the sulphurs to carbon and all the zincs to carbon, I'd have diamond. So I want you to recognise that parallel between diamond and zinc blend. Now the properties of diamond result from that structure. It doesn't conduct electricity because the electrons are locked in those sigma bonds. It's a good conductor of heat. It has a very, very high refractive index, and that's responsible for the brilliance of diamond, and that's why diamond's used in jewellery. And it's extremely hard. It gets a 10 on the Mohs scale, so the higher something is on the Mohs scale, then it's able to scratch anything that's below it. So quartz is 7, calcite is 4, which means diamond can scratch quartz, diamond can scratch calcite, and quartz will scratch calcite. Very hard material, which arises from its structure. Okay, last slide. This is Lonsdale-lite. This is a very rare form of carbon. It's commonly found in craters where meteorites have hit the Earth. And this is related to wurtzite. So diamond is related to zinc blend, and this one's related to wurtzite. Now, the atoms are eclipsed along one direction only. So we have the staggered bonds here. So these bonds in this plane are staggered, but along this direction here, and only this direction, the bonds are eclipsed. So if you look at these two carbons here, the carbon there is directly above that one there. The carbon here is directly above that one there. And that carbon directly above that one. So in one direction only, we see the bonds being eclipsed in that case there. But it's only found in meteor craters. Now, if you look at the hydrogen bonding in ice, we've got exactly the same sort of structure. So ice, wurtzite, Lonsdale-lite all have the same type of structure. Okay, so that's a good point to leave it there for today, and we'll continue on with this very exciting story of carbon in Friday's lecture. Thanks for your attention, everybody. See you Friday.
Do you have any resources you can recommend to help visualize these three-dimensional?
So, yeah, can you fit this week? So you can go to more than one fit, but you're going to actually have models to play with, and that'll give you a bit of that feel for how what we mean by using it against the site. So don't worry too much about it until you get to actually do the
construct electrolytes or picking the makes sense.
What is the exact difference between crystal and glass?
Yeah, so in crystals there's a repeating unit, a regular repeating unit, whereas in glass it's a very much absorbed sort of no repeating structure.